Good afternoon. My name is Larry Gabka. I'm a biology instructor here at Gabka Community College. And our Dean of Instruction, Ken Traska, asked me to speak to you a little bit today about how I can engage students in the classroom. There's been a lot of interest lately in student engagement or making an active classroom rather than just a straight lecture. Now, before we start, let me preface this by saying I love lecture. I like to go to lectures, I like to listen to people, and I like to give lectures because I think you can get a lot of information across in a short amount of time if you have a good speaker. All right? In the hands of the wrong speaker, lecture is death. So I'm going to try to stay away from that. But anyway, so let's talk a little bit about student engagement. As I said, I'm a biology and sometimes chemistry instructor here at Gabka Community College. And we are here in the biology lab. And if we're talking about student engagement or hands-on learning for our students, I mean, what better place to be than in a laboratory? We have equipment and things for the students to do. But I'm not here to talk about laboratory activities. I want to talk about what we can do in the classroom to make the classroom a little bit more dynamic or engaging for the students. By the way, one last little disclaimer. I've had 3 minutes notice to do this, so there's been no prep work whatsoever behind us, so here we go. All right, student engagement. We had a speaker here a couple of years ago who came to the college and talked to us. His name is Mark Taylor. You can find him on the internet. He has a lot of interesting things to say. Mark Taylor does a lot of work with around the idea of Generation Next, and talks a lot about how our current students are very different than we are in terms of the way they were brought up. They were brought up more with technology, computers, video, whereas the older generation, we were more. My mom used to go buy a pile of old boards and throw it in the yard and say, go build something, right? Okay, well, so growing up, the students that we're getting are very different than we were. So his argument is that students learn differently as well, and to just give them a straight lecture doesn't really engage them and do the job for them. He goes a little bit further than I would, however. Whenever I listen to him speak, one of the things he says you should do is get all content out of the classroom and only talk about application in the classroom. Like I said, I love lecture. I can't go that far. All right, it's just not in me. All right, but I think there are some things you can do to combine presenting your material with activities for students to get them more involved. I'm a biology teacher. Mostly what I teach is molecular and microbiology. I love models. All right, here I have a model of a sugar molecule, glucose. All right, and we do lots of things in class with these models. I have the students start from very basic, simple chemical structures, and I have them put them together. I name molecules. I have them build molecules from the names and see if they can name a molecule from a structure. Things where they actually have to go and put it together. It takes a lot of thought for the students to look at this collection of plastic here and actually understand what atoms are where, how they're related, how it's going to behave as a result of its structure. So I do a lot with these, and we'll see a little bit more about that. Hey, why don't you look at the wall behind me? All right, this is something I have the students do. This is, if you look at the whole wall here, I have a biochemical pathway. This is one of the central themes in biology is metabolic pathways, and how we take molecules like glucose over here, which is what I showed you, how we take that sugar molecule and actually use it to generate some usable energy in your body. You take this glucose and it goes through this whole series of reactions. And at first, when the students look at this, they look at it and say, wow, what a complex mess. Give to them a piece of paper It looks something like this. And they say, I can't do anything with that, right? So it's all very, very complicated. But when I have the students build it, we build one molecule. We start with that glucose. And then I say, okay, something's going to happen to this molecule. All right, something's going to happen. An enzyme's going to come in. It's called hexokinase, and an ATP molecule comes in. And we talk about the changes that occur and how this kinase, this enzyme, what its role is to transfer phosphate groups. And we transfer phosphate from this ATP to this glucose, and we end up with this new molecule. So I just think back to when I was in college learning these biochemical pathways, memorizing names of pathways, not getting structures. As soon as we build it, we can see how one molecule is different than the other. We start with one, we make a small change. We make another small change. Incremental steps all the way through the whole process. And by the time we're done, the students can actually use this. Now, the other thing I do is I don't make my students memorize this. When it's time for the exam, we actually come in the lab, and they get to add stuff to this model. You know, I take it down every year. They have to rebuild it. They can add stuff. They can change it. Different classes do different things for symbols and structures. But every group gets to change it and make it their own. And when we're finally done with it, they sit down, they take the exam. They take the exam in here. And they can wander around in here. And what I tell them is, if you've done your job, all the answers are here somewhere. So if you've done your job and created this model set, and you understand what it's actually trying to tell you, the answers are there. You don't need to memorize all the stuff. All right. Also, on the theme of biochemical pathways, we talk about how at every step in this pathway requires a different machine, a different tool, something to make it happen. And of course in biology, those tools, those machinery of your cells that make all these pathways happen are called enzymes. Those enzymes are written on each of these arrows. And so another way to illustrate what a biochemical pathway is for my class is I talk about the concept of assembly lines, where in an assembly line you start with the raw material and you send it through a first process. The machine gets a hold of it, changes it. Then you have another machine that changes what was the first machine left. We go through this whole process. And what I like to do in my class, let's start with something simple. I give them a piece of paper. And I put them in a line of 5 students. And I assign them roles. Each student is an enzyme, right? And each student will then go and have one job. Right? First student will have a job. The first student recognizes this as his raw material. And that first student has one job, and that job is to simply fold this piece of paper in half. And that's the only thing that student knows how to do. All right? So I tell that student, okay, that's your job. So anytime I give you a piece of paper, you fold it. That's all you know how to do. Just like whenever this enzyme, this hexokinase, gets a hold of the glucose, puts a phosphate on it. That's all it knows how to do. It does one thing, does it very well, does it very quickly. So that's its whole purpose. And so when I get back to these biochemical pathways, I tell the next student in the line, your job is to simply what? Fold the front of the paper down. I think I know what we're going to do with this, right? The second person folds this paper in half this way. And that's all that person knows what to do. If I were to give this piece of paper to the second person in the line, they wouldn't know what to do with it. Their only job is to take a piece of paper that is folded in half like this and turn it into this. Right? And I guess, you know, the idea is to have the students doing something. Third person in line, of course, is going to fold down this part a little bit more. We're almost there. All right? So that's the third person's job. That's all they know how to do. And the fourth person has a very important job of folding the tip back here. And then the fifth person has the job of final folding these wings down. All right, and when that fifth person's done, they get to sort of the class. All right, now, what we've done was, I'm trying to get across the concept of what is a biochemical pathway. And I can tell them over and over, a biochemical pathway is a series of chemical reactions leading from a starting molecule, a resource, towards a final product. And that series of chemical reactions is controlled by a series of enzymes. Well, each person in this process was an enzyme. The resources started with just a flat piece of paper here, and when we were done, we had that airplane. From that concept of biochemical pathways, now everybody understands what a biochemical pathway is. From that one simple concept, we can now talk about how do we control this pathway? Where would be the best place to stop this pathway if we need to stop it? You know, you don't want to do everything all the time. You know, what if your cells decide they have enough of a certain product? Well, they need to shut the process off. Where do they shut this process off? The best place to shut off the process is of course, before you even start down the pathway. So I talk to the students about, hey, here's this piece of paper. What can I do with it? You know, I could write a report for my boss. I could type up an exam. I could, you know, make a paper airplane. I could do lots of things with a piece of paper. I could start a campfire. But once I change it, once we make that first change, this is no longer acceptable to write a report on, send my boss. It's different. It's not a nice flat sheet of paper. It has been altered. It has other purposes, but we don't want to waste it. So when I talk to them about these pathways, I talk about how can we shut this off, and what we end up doing is shutting it off here at the very first step of the pathway. At the very first step, before I fold that paper to start making a plane, I end up stopping the process. That way, at least I can use that paper for something else. And the other question comes in, how do I know I have enough of this product, so I should shut this process off? And the really fun and interesting thing about that is that it's the product. When enough of these accumulate, they're used as a signaling mechanism to shut off the beginning of the process. So what I do with my students is I give them a big stack of paper, and I have them run this assembly line. They're making, you know, 30, 40, 50, 60 paper airplanes, and they're starting to stack up by that point, and at some point we have to say enough. And so when there's enough paper airplanes, one of those paper airplanes, I go and I attach to one of the students. You know, you put it in your hair, on your shoulder, in your pocket. And when that plane is attached to that first student in the pathway, the person folds their hands. So what happened? It didn't stop my process. It didn't stop the pathway for the stuff that already started down the line, but it stopped new molecules from coming in. And so when we've used up all the paper airplanes, the last one we use is the one that's attached to that student, and we go back to work. And so from something very complicated in the cells, something that's a very complicated process, having a biochemical pathway, having the machinery in order, running this process, the students can gain an understanding of how the process happens, and more importantly, how we can control the process. And we can illustrate it with all kinds of little things. I've done this with, when we talk about protein synthesis. I take some tape and I put it on the floor in the shape of a ribosome. I have the students in the classroom have this big long DNA molecule, and I have students making RNA molecules from that. And then every student becomes a transfer RNA molecule. And I have them floating into and out of the ribosome. And if you're interested, call me up. I'll show you one day what that actually looks like. It's actually kind of funny, because I have all the students with amino acids taped to their arm and anticodons taped to their feet, and they all have to walk around and float around, and if they float into the ribosome and they're the right transfer RNA, they'll be locked in place and we'll start building this protein. That exercise takes about 45 minutes to get through, and I'm certainly not prepared to do that today. But if you're a biology teacher and you're interested in that, give me a call. So anyway, I guess my final thoughts on active learning is, first of all, again, I love lecturing to students. In fact, if Ken, who's holding the camera, by the way, would let me, I would run my biology class in 48 straight hours continuously, start to finish, and be done for the semester, but he won't pay me for that. But anyway, I love the lecture, but I also understand that my students don't always love to sit and listen to me. Who knew? Anyway, so what I try to do is every day there should be at least one thing in there somewhere where my students can put their hands on it or make it. Primitive is good. I like primitive things like paper airplanes or models. They don't have to be purchased models, but I like things where the students have to be a little bit creative. And if it can help them retain the material, the information, great. So anyway, I guess that's all I have to say. So thank you very much. Have a great semester. One other word. In addition to a faculty member, I'm also your AQUIP coordinator, which AQUIP is our model of accreditation. And so I'm sure I will be contacting you somehow during this year, looking for feedback and information from you on your experience and in class and a variety of things in your experience with the college itself. Because this is a big year for us, and enjoy your year. Thank you very much.